Linked list, we have now made it to deleting nodes. Let's go. Going to be fun, hopefully relatively pain-free. As we like to normally do, let's start this out with a couple of review questions. Firstly, what is the big O running time to insert a new element at the beginning of an array? And we qualify this by saying, while keeping all of the current elements of the array and also keeping them in their relative order. But in short, just the big O running time of inserting a new element at the beginning of the array. Pause the video, see what you come up with. The answer is simply O of n. We need to shift over all n nodes in order to make room to insert this new element at the beginning of the array. What is the big O running time to insert a new element at the beginning of a linked list? Same thing, keeping all nodes in the list, keeping them in that relative order. Pause the video. What's the answer? Answer here is why we use linked lists. The answer is O of 1, constant time. No shifting is required. In fact, all we do is we change a couple of pointers of addresses as we have seen, right? This new node that's going to go to the beginning, it's going to point to the previous first node, and then the head is going to store the address of this new node. So effectively, two addresses are saved or changed, and that's it. No shifting, constant time, which we call O of 1. It doesn't mean it takes 1 unit of time. It just means that it's a small amount of work. It's a constant amount of work required. What is the big O running time to insert a new element at the end of a linked list, assuming that we only have access to the list via our head pointer? What is the big O running time to do that? Inserting at the end of the list. Pause the video. Here's the answer. Answer is O of n. Why O of n? Because we need to traverse down the entire list in order to insert at the end of that list. We need to traverse all the way to that last node and stop at that last node from which we therefore do the insertion. Lot that we can do on linked lists. Insert nodes, delete nodes, traversing and doing all kinds of stuff. Well, we are finally at delete, and this is going to be pretty straightforward because delete really amounts to what? Find the node that you need to delete, but we're going to start by finding the predecessor of that node and then just change a single pointer, change a single reference. You're going to see how easy this is. So starting point, search for the node that you actually want to delete in the list. And if we find that node, delete it. Shocker, right? We're deleting. If you find the node, actually go delete that node. This means that we're going to be changing the addresses. We're going to be changing what's saved in the next of a particular node, the predecessor, in fact. So the summary is, find the predecessor of the node that you want to delete, and then make that predecessor point over to the successor. The 4 scenarios of deletion are as follows. You could be deleting the first node of the list. You could be deleting the middle node of the list. You could be deleting the last node of the list, or I say here's a special case where you're really deleting the only node of the list. And this will, of course, cause head to therefore point to null, indicating that the list is in fact empty. Here's some pictures of each of those. Deleting the first node of the list. Imagine we wanted to delete this 4 here. That's the node we're deleting. This is the result. Super, super exciting. And here is some more details. How do we make that happen, right? Think about this. If we want to delete that first node with a 4 as we see here, head needs to point over to this second node in the list, which means we need to take the address of this second node and we need to save it into head. Where do we get the address of that second node? The address of this second node is found where? It's saved right here in the next of the first node. So we want to take that address, which is the address of the second node, and we want to save it into head. This is what we get. And when we save that address into head, I'm going to do it again. I love the animation. We save that address into head. The consequence is head now points directly to that second node, we have bypassed that first node. No one is pointing to that first node, the consequence of which is what? Java garbage collector has zero mercy, and it will immediately delete that first node because no one's pointing to it. Delete a middle node of the list. Imagine we're trying to delete this node with the value 6. This will be the result. Once again, think of how you made that happen. This node number 4, the one that has 4 as the data, it needs to point directly to node number 8, the one with 8 as the data. So we need to save the address of this node 8 into the next of the node that has the value 4. I'll call it node 4. So save the address of node 8 into the address of the next of node 4. Once again, how do we make that happen? Where do we get the address of this node 8? Or who in particular currently stores, or what variable stores the address of node 8? The answer is the next of node 6. Right here, this little blue box, that is the address of node 8, and it's pointing therefore over to it. Take this address and save it directly into the next of 4, the consequence of which is 4 points directly to 8. Or you could say in specific, the next of 4 points over to node 8. We have bypassed node 6, and that's really how it gets deleted. In Java, since we have a garbage collector, that really deletes the node. The garbage collector does the deleting, but what allows that garbage collector to actually delete it is the fact that it's no longer being referenced. Nothing is pointing to node 6. What was pointing to node 6, node 4, is now pointing directly to 8. 6 has been bypassed. Java garbage collector, no mercy. 6 is gone. Delete the last node of the list. What happens here? We want to delete that 8. Here's the resulting list. How do we make that happen? Once again, we need to now save this null that's right here. We need to save it into the next of node 6, thereby allowing us to bypass node 8. So where is null currently saved? Well, it's right here. It's in the next of node 8. We need to save it into the next of node 6. Make that happen. 6 will point directly to null. Java garbage collector, no mercy, 8 is gone. Here's the final case of deletion, deleting the only node of the list. Once again, how do we make that happen? We need to save null into our head, bypassing that singular node here, node 7. Where is null saved? It's saved in the next of node 7. So we're going to take that null, we're going to save it into our head. It's going to get saved into head. The result is that head now points directly to null, and 7 has been, or will get deleted by the Java garbage collector. That's a quick time for a brief interlude, but we'll take it. Right turn only. Is that a fail? Yeah, it's a pretty bad fail. And one more, programmer meme. This is great. When you write 10 lines of code without actually searching for an answer on Google, it ain't much. But it's honest work. It is honest work. Let's go. Let's examine the code. That's why we had that little interlude there, because now we're just going to jump right into the code, and here it is. You can pause the video, see if you can make sense of that on your own, but we're going to go over this in detail. We have a delete method. We're trying to delete a particular value from our linked list, which means we need to first and foremost make sure that we have a list. If the list is not empty, which is the first part we're going to examine right here, in detail, you can't delete unless there's a list. So that's what this is checking, making sure that we actually have a list. If we do have one, if we have at least one node, let's go ahead and enter this if statement, and let's try to check if we can find that node. So here we first have another if statement. We have to examine the condition of whether or not the head is pointing to the node that we want to delete. What if the node we want to delete is actually that very first node? That's what this if statement is doing. Head is pointing to the front of the list. So this if statement says, hey, if the value that we're trying to delete, if it actually is head.data, If it's the value that is found in that first node, we need to execute what is inside this if statement and delete that first node. So what do we do here? If this is the case, this head.next says take whatever that first node is pointing to. If it's pointing to the second node, then we'll take the address of that second node and we'll save it into head. Or if the first node is pointing to null, we'll take null and save it into head. Take whatever that first node is pointing to and save it back into head. Take the address that is in head.next, which is whatever that first node is pointing to, and save it into head. So head will now point to the second node if there were multiple nodes in the list, or head will point to null if there was only one node in the list. Either way, we just bypassed that first node. And once again, here the same graphic we already saw. We have this scenario, delete that first node. This is the result. We said, how did we make that happen? We need to save whatever is in the next of that first node. And notice this would be head, would point to the first node, dot next. So head.next is the address that is in the next of that first node, and we need to save it back into head, which is why we have that line of code, head equals head.next. This is the result. We just bypassed that first node. Or if the list was empty, head would now point to null. So now we have an else. What is this else actually doing? We'll back up to what did the if do? The if was checking if the value we're looking for is the first node. If that value we're looking for is the first node, delete it. Else means the value we're looking for has to be somewhere else inside the list. That is, if it's even in the list at all. So now, if we can find this value, if this node is in the list, we need to now traverse over the rest of this list. That's a great blooper. I'm not even going to delete it. Here we now have an else. LL node, help pointer equals head. What's the purpose of this here? Well, if we need to traverse our list to find the predecessor of the node we want to delete, well, traversing, you need a help pointer, right? And you need a while loop. So we make a help pointer and we save the reference of head into this help pointer. And then we traverse using a while loop. And notice the condition of the while loop here. We have while help pointer dot next does not equal to null. We've seen two conditions previously. We've seen while help pointer does not equal to null, which was used when? We use that whenever we want to traverse over the entirety of the list, and we don't mind help pointer going to null. But when we want to insert, you likely recall that we said while help pointer dot next does not equal to null because we needed to stop at the predecessor in order to make the important connections. Well, in that same way with deletion, deletion happens via the predecessor. So when we're searching the list looking for our node to delete, we actually need to search via the predecessor, and you'll see how this works. So as long as help pointer dot next is not equal to null, we're going to traverse the list. So specifically this while loop, it's going to check to make sure that the node that comes after whatever node help pointer is pointing to, that node is not null. Why? Because we want to stop traversing at the predecessor. So the deletion of a node, it really amounts to what? It amounts to changing the next of the predecessor and making it point to the successor, the node that would have come afterwards. Additionally, inside this while loop, and we're going to see a graphic in just a moment, inside this while loop, what do we want to do? We want to actually check the data value at one node after where help pointer is pointing to. Imagine help pointer is pointing to node number 12. Well, we want to check the data value of node 13. Remember, node number 12 on that example would be the predecessor. We want to check the data value of one node down the list at node number 13. Well, we have to first make sure that node exists. We need to make sure it's not null before we ask Java to actually go test its data value, because otherwise we would have an error. So again, we always look one position after where help pointer is pointing to. Why? Because we need to stop the traversal at the predecessor node, allowing us to connect the predecessor to the successor. It's a lot of words. It's going to make sense in just a moment. And now we have a lot of stuff in here. We have an if statement. Inside the if statement, we do some connections. Let us make sense of this in detail. So we're actually going to move this entire block up, this entire if statement here up to the top with that while loop to see. While help pointer dot next does not equal to null, we're going to keep traversing down, making sure that we have not reached that last node, because if we reach the last node, we're going to stop the traversal. And what do we say inside this while loop? We say if help pointer dot next dot data equals value. Why is that? So there's two main parts of this while loop. We have this if statement and everything inside it. Get excited for this amazing animation here. Woo! There's the if statement. The if statement and the stuff inside it, what's going on with there? That's checking to make sure that a particular node has the target value. That's checking to make sure that some particular node has the target value that we are looking for. If we find that node, we need to bypass it. We need to make the predecessor point to the successor directly. And then, of course, we're going to break out of the loop. Now, if we don't enter that if statement and we have not yet found the node that we're looking for, take one more step down the list. Awesome animation. By the way, that is sarcasm intended, right? That is hideous animation. If this were a professional presentation in front of a group, you should never, ever be having your stuff circle around like that. I like to play in silly ways with animation. So if we do not enter that if statement, take one step down the list. Full disclosure, I know that this is confusing when we hear this the first time, which is why we really need to see an example. We're going to do that now, and we're going to come back to the code. Let's go through this step by step. So I say here, imagine we're trying to delete the value 30 that we can see right here inside this list. Let's walk through this while loop and make sure we understand it completely. So we have here while help pointer dot next does not equal to null. Let's look at what gets highlighted now. Help pointer, this entire help pointer turns blue. Help pointer is currently pointing to that first node. It turns blue, but it's not just help pointer, it's help pointer dot next. So while help pointer dot next, so that points actually to the second node. We want to make sure while help pointer is pointing to the first node, we want to make sure that the second node is not null. That's all this is doing. I'm going to back up again. While help pointer dot next is not null, we're making sure. So 20 did a little dance there, right? Because we want to make sure that it's not null. It's not null. It's clearly a valid node. So now we can enter into the while loop, and we now perform this line of code. If help pointer dot next dot data is value, we're basically checking, hey, is this 20 equal to the 30? So it's going to look. We're now looking at the 20. Is that 20 equal to the 30? It's not. It is not equal to the 30. So now we do not enter that if statement, and we come over to this line of code, which we're experts at. Take one step down our list. So now help pointer is pointing at the second node. Let's continue. While help pointer dot next does not equal to null, so we're going to look at one node past where help pointer is pointing. Help pointer is pointing to the second node. So the help pointer dot next does not equal to null. We're going to be checking the value of the third node. We want to make sure that the third node is not null. So do that again. Help pointer dot next, it does not equal to null because you can see this node with the value 30, it's dancing. It's an actual node. Cool. Enter the while loop. We now do the if statement again. If help pointer dot next dot data equals the value we're looking for. Well, we're looking for the value 30. Help pointer comes to here. Dot next comes over to here. dot data, we have now found the value we're looking for. So what do we need to do? We need to execute this line of code. But let's be very clear here. The goal was to delete 30. We found 30, but when we found 30, at that moment in time, where's help pointer pointing? Help pointer is pointing to the predecessor, the node that comes before 30. So when we want to delete 30, the traversal will stop, not at 30, the traversal will stop at the node before 30, which is the predecessor. And that should make sense because from that predecessor, we're going to make the connection to skip 30, to bypass 30, and point directly to 40. So help pointer.next.data, the consequence of which we found the value we want to delete. We can now enter this if statement and we can perform the deletion. Let's head over to the tablet and look at this in more detail. So now that we're here and we want to perform this deletion, I need to delete this node 30 right here. That's what I want to do. So let's make sense very briefly. Let's try to make sense of how we're actually going to do that with this line of code. So since we just entered the if statement, we're really trying to execute this line of code right here. And of course, this is an assignment statement, so our eyes should come to the right side of the assignment statement. And let's make sense of what this is saying. It says, let's go to help pointer dot next dot next. So help pointer is right here. So help pointer comes to here. Dot next is, well, you can't see that because of the color. Let me change the color here. Back up, do blue. So help pointer comes to here. Dot next brings us over to this node. Dot next brings us over to this node. So the question I could ask would be, what is actually stored inside help pointer dot next dot next? That's a good question. What is stored inside help pointer dot next dot next? The answer is the address of this node with the value 40. That's what is stored inside help pointer dot next dot next. Or you could say, where is help pointer dot next dot next? The answer is right here. That's help pointer dot next dot next. It's this address right there. And again, one more time, because it's very important to me to do this. Here's help pointer. It brings us down to this node. The first dot next is right here, which brings us over to this node. And then here is that other dot next, that second dot next. So the question you can ask yourself, now that we found the dot next, and we see that this is the second dot next, right? Help pointer dot next dot next. This is the second one right here, right here. So what is stored in that address right there? What is stored inside help pointer dot next right here? The answer is the address of the last node. So now that you know what this is referring to, help pointer dot next is referring to the address of the node after the node that we want to delete. Perfect. What do we want to do with that address? We want to save the address of this node. We want to save its address right here because we want 20.next to point directly over to that last node. So we already understood what? We understood that this right here, help pointer dot next is the address of the successor. That's the easiest way of saying it. Help pointer dot next refers to the address of the successor. And for clarity, when I say successor or when I say predecessor, we're saying that from the perspective of the node you want to delete. So this is the node we want to delete. Its successor, its predecessor is 20, and its successor is 40. So one more time, help pointer dot next is referring to the successor node, and we want to save the address of that successor node into the next of the predecessor. We want to save it right here. And where is the address of that successor node found? The address of that successor node is found right here, which is help pointer.next.next. And we want to save this address. We want to save it right here into help pointer.next. So help pointer.next.next takes the address of that 40 node, the successor, and we're going to save it directly into help pointer.next, the result of which is 20 is going to point directly over to that last node, and we're going to get this. And then this will get deleted. Is that helpful? I don't know. I think the picture is very helpful, but we're now going to go through this one more time. Come back here to the pictures, and we're actually almost done. This is what happens. So now help pointer equals help pointer.next.next. I just explained that in detail on the tablet. That's what you get on the slide. We're executing that line of code. Help pointer comes to node 20. .next comes to node 30. .next, which is right here, it stores the address of node 40. Take that address and save it into help pointer.next, making the next of 20 go directly to 40. Done. So in detail, we've already given the explanation. I should better read through this pretty quickly. What's obvious is we're checking if some data value is equal to the value we're looking to delete. But what data value or what node? Help pointer.next.data says to look at the data value in the node immediately following the one that help pointer is pointing to. So if help pointer is pointing to node 87, help pointer.next.data says look at the data value in node 88. And we're going to compare that to the value we would like to delete. So hypothetically, if the target that we're looking to delete is found at node 12, does help pointer at that moment in time point to node 12? Pause the video, think about that. If our target that we're looking to delete is found at node 12, does help pointer point to node 12 at that moment in time? Pause the video. The answer is absolutely not. At that point in time, help pointer is pointing to node 11. Help pointer is pointing to the predecessor. If you find the value that you want to delete at node 12, you did that via the help pointer, which is pointing to node 11, and then we checked its next .data, and we arrived at node 12, and we found it there. But the help pointer would have been pointing to node 11 at that moment in time. So inside the if statement, we want to look at the code. So one more time, the if statement says, if the data at the node following the one that help pointer is pointing to is equal to our target value, we enter that if statement and we perform those two lines of code. That first statement is this one. Help pointer.next equals help pointer.next.next. Your eyes should see the assignment. You should look to the right. You should focus right here. Help pointer.next.next. It says look two nodes after where help pointer is pointing to, take the address of that node and save it into help pointer.next. What does this do? It effectively bypasses that node that we want to delete. So if help pointer is pointing to node 11, help pointer.next.next is pointing to node 13, this line says take the address of node 13, save it into the next of node 11, making 11 point directly to node 13, skipping node number 12. Finally, you break out of the loop because we already found the node we wanted to delete and we deleted it. We skipped it. Java garbage collector really deleted it, but we bypassed it. And now we break out of the loop and we are done. So one more time, let's look at that picture and make sense of this. But this code took care of all of it. The two cases of deleting a node from the front or deleting a node from anywhere else in the list. And now I'll come back to the pictures. So once again, we want to delete the 30. While help pointer.next does not equal to null, 20 is not null, it's a valid node, so we enter into the while loop. We looked at the value, we looked at the node after where help pointer is pointing to, right? While help pointer.next is not equal to null, we enter this while loop, and now we have an if statement. If help pointer.next.data is equal to the value we want to delete, 20 is not equal to the 30, so we do not enter that if statement. The if condition is false. We take one step down our list. We move help pointer to point over to node 20. Back at the while loop, while help pointer.next is not equal to null, this node right here, help pointer.next, 30 is not equal to null, it's an actual node. So now we're going to what? We're going to enter the loop, and we're going to check the if statement. If help pointer.next.data equals the data of the value we want to delete, then we need to enter that if statement, and now we're ready to actually skip or delete, bypass that node. So what do? We take help pointer.next, which brings us to this node, node 30.next, that's the address of 40. We take the address of 40 and we save it into the next of 20, which is accessed via the help pointer. So it's help pointer.next, and we get this. That is our deletion. So what we've covered thus far, traversals, printing linked lists, modifying linked lists, counting the nodes of the list, summing the nodes of a list, all kinds of traversals. We've covered adding nodes. We've covered deleting nodes. In the process, here's all the traversals. We covered all this traversal stuff. Well, guess what? We are done with traditional regular linked lists. Got one more short video to come. I call it Linked List Madness, where we're going to visit circular linked lists, doubly linked lists, and circular doubly linked lists. Going to be fun. Until then, take care, everyone. Was it amazing? I don't know. Got a great demotivator. Consistency. It's only a virtue of being consistent if we're not consistently screwing up. That's actually a good one. I like that one. Take care, everyone.